So the question was, what is Fock space? Since the majority of the people are mathematicians, I will give an answer which is not historically. Historically, Fock space was introduced in physics, but we have deduced the Fock space, the space to understand from mathematical point of view what is Fock space. Remember that I always studied the pre-Hilbert space, the polynomial algebra as a vector space. As a vector space applied to the vacuum. The polynomial algebra applied to the vacuum gives a vector space. And all our lectures have been discussing this kind of thing. The usual definition of Fock space can be seen so. If I take the norm closure, this will be the Fock space. The Fock space over the space. See, here we have a random variable x. The random variable x is equivalent to its probability distribution. Its probability distribution has all moments, therefore it is equivalent to the pair of sequences. Jacobi sequences. Okay, so with this we have what in this is the gamma L2 of R in the notation of Professor Lu, this is what Professor Lu calls gamma of omega n. explicitly write n goes from 0 to infinity. Now, no longer finite linear combination. Now, infinite series. But the infinite series must converge. So we have such that the norm of this vector but you know that we have proved that the orthogonal polynomials are orthogonal. That is why they are called orthogonal polynomials. So this is equal to what? This is equal to this. But we have proved in my lecture, not proved, but I have shown you this theorem which says that this norm is exactly omega n factorial. So we want, so this norm here, square norm, is equal to the set of the infinite sum from 0 to infinity x n omega n factorial. Okay. So x n squared, because the is squared. Okay. So this is what? X now is a number. X are numbers, complex numbers. So how can we write this? We can write as Euclidean scalar product in C. The complex number is a hyperspace with gamma of omega n. One more interacting process. See? So this gives you the full connection. Okay.
Thank you very much. I want to request that you give us your lecture notes on this Jacobi sequence. This the one you did this morning. That you should give it to us.
It is in the notes you already received.
Well,
There is proof of that.
the Jacobi
The
sequence
notes contain all that.
is there. I requested because I observed that this approach is a generalization of Padasarati's work. With Padasarati,
Patasarati is
a special case.
no, it's an infinite dimension. I am now doing,
Okay.
you see, this is I wrote here. Patasarati, I am now doing the quantization of say Hasselbalch-Lazarani scheme is a gamma of I am doing L2 with complex values. And the Hasselbalch-Lazarani scheme is this L2 of R. In fact, they take R plus with the positive real line with values in another space. So I take with values in the longer. Of course, this theory is true, but the reality is the Hasselbalch-Lazarani scheme of the stochastic calculus is infinite, in one sense more general because it's infinite dimension. In one sense more particular because it can deal only with Gaussian. Okay? It doesn't include the infinitely many, uncountably many measures that we include. We will go to the infinite dimension. We can deal with this, but the notation becomes more complicated. So I want to, as I said in my introduction, I want to describe what happens in the simplest case of square integrable function with values of the constant, not in an infinite dimension.
So what I observed in his presentation, in Padasarati presentation, is that he started with the pre-Hilbert space, which is the space of exponential vectors. Then he defined on that the inner products that we will be using, and after doing that, he was able to relate it with the while commutation relation.
That is different.
Yes, and then the completion gives the
Let me
form
explain.
space.
Let me explain. You see, this is again very, very special. There are many formulations of Heisenberg commutation relation. Heisenberg commutation relation. There are many formulations. these other operators, they are again, but these are very subtle technical points that I am avoiding because I am going to the conceptual innovation. Okay? There are many inequivalent, but these are for technical reasons, related to unbounded operators. And the feeling of my course is to explain to you the conceptual innovation, which are, in my opinion, more important than the technical points. Okay?
Then I have seen this definition before in Obata's work, in the introduction of the white noise of workspace. He called those omega nets the weight sequences.
Obata
began
to work on this
approach.
Yes, he began to work with this because in the theory of white noise, many researchers, not but essentially the German school and the Ukrainian school, Kondratiev and many other Ukrainian mathematicians, they introduced by hands what Professor calls one-mode type interactive form. You see, by hands. But and there exist three types of interacting forces. And what they introduced, and Obata took from them, was type 1. Then there is type 2 and type 3, but we will not discuss these three types in our lectures. Okay? So just to have the full picture. Because you see, this normalization, why there is this wave that appear in the scalar product? Because I am taking the monic polynomial, not the normalized one. Remember, normalized one means monic polynomial divided its norm is by definition, and I denote with not phi n but phi tilde n. These are normalized. And in white noise they use not also the monic, so it appears this, but only for Gaussian. And then Stride, Kondratiev, and Berezansky, many began to look for. Berezansky was the first to say, let us put omega n, principal Jacobi sequence, and he calls Jacobi. And this is what Obata used. But this is only one type, what the simplest model, what Professor Wu calls one-mode type. And this morning, Professor Wu in the lecture shows that one-mode type is not sufficient to obtain all what we want to do, that is to represent the stochastic independences of quantum probability. Okay? So there is a logic that brings all these things together. There is a question. There is a question. Very interactive Fock space. Well, you see, there are also several types of Fock spaces because there is, if you take a sequence of Hilbert spaces, Professor Wu explained very well this part. If you take a sequence of Hilbert spaces, then we can define in each Hilbert space has its own scalar property. Then the interacting Fock space the interacting Fock space is associated to these sequences. Now I fix this sequence. And this, by definition, we call gamma equal by definition sum and you have, this is called interacting Fock space over a pre-Hilbert space H. Let me call it for future. So interacting Fock space is first, you have to give this. Second, you have to give a linear map, which we call a daga, which to an element of this K, this associate a daga F, which belongs to the linear adjointable operators over gamma. This morning I have defined what means adjointable. The adjoint exists, okay? And this is the this is a linear map. And this we call creator map. Okay? Now, this is interacting Fock space. General. Then you have this is general interacting Fock space. Now you have full Fock space. Full Fock space is a particular case of interacting when Hn equal k to the tensor power n for each n, and the scalar product is what in the lectures of Professor Lu is indicated with tensor n. What is this scalar product? This scalar product is k tensor power n, then A dagger F applied to capital F by definition will be F tensor capital F. So this is the creator in the full Fock space. Okay? In the boson Fock space, the boson Fock space, H is similar, but what is the difference? Hn is not the usual tensor product. It's the so-called symmetric tensor product. So K is, and the symmetric tensor product is defined by power n. What is the symmetric tensor product? Symmetric tensor product is the subspace of the full tensor product generated by the vectors of the form F tensor power n. For each F in K and for each N. And for each. That is true for every N. Okay? This is the boson Fock space. What is the creator in the boson Fock space? The creator in boson Fock space is A dagger F, like this. If you have now, here belongs to K to the tensor power n, but in the boson case we have symmetric tensor power. So capital F will belong to the symmetric tensor power. Symmetric is denoted by an index head. If I take power of the same test function, I don't need the heads because they are all equal automatically symmetric. Okay? So this is K head n, and AF applied to capital F is by definition the symmetric tensor product, of S times capital F. So you see, the full creator is just the tensor product, only the first element. Here F, for example, if F is equal to this, let us say capital F is equal to G to the tensor n, like this, with G instead of F, symmetric. This is symmetric, obviously, because it's the power of a single test function. Then, so, example, if well, it's a more complicated structure, but there are many what I want to talk.
Fog
module is another story. No, that is another story. No, module is another story. Is different. The scalar product is value is an algebra, not in the complex numbers. Okay, that is module. But finite type of space is another. It's essentially Fock tensor anti-Fock. Essentially, you can replace the theorem of Araki that says that you always represent it this way. Okay, so you see there. This should give you the perspective. Interactive for space is the most general space which has a Hilbert space, or pre-Hilbert if you want, that has an orthogonal gradation, and it has a creation operator, which is adjoint operator. The adjoint operation is called annihilation, but it can be complicated. Depends on the scalar product. You see, not always. If I take arbitrary sequence, not always. Well, to make the full connection, let me give you this theorem. It was in 1998. Professor already mentioned it in the paper of myself in Boteco in 1998, which gives the following theorem. So, remember, I gave the definition of Hn. And we now have interacting for space, but we can say that, you see, here, the point is, we can have interacting for space which have the same as full, the same as boson, but differences here. Okay? So we can have full interacting for space in which Hn is like in full for space, namely tensor product of a single one particle for space. But the AF is not the usual full creator. It's different. That was origin. You can have symmetric interacting for space. Professor Lu already mentioned this. You can have symmetric interacting for space in which Hn is again the symmetric tensor product. But it's not boson. Why? Annihilator is different. Creator and therefore annihilator are different. The theorem says, what is the theorem? The theorem says, you see, if K is just the complex numbers, which is a Hilbert space for the Euclidean scalar product, then there is no difference between full and symmetric, because there is no difference. You multiply one thing for by itself, only one vector. Okay, there's no difference. Okay. So the theorem that we proved in 1998 that was at the origin of probabilistic quantization is the following theorem. If the Hilbert space K is reduced, is identified to a one-dimensional Hilbert space, so is isomorphic to the C. So the condition that the norm of the zero is 1 uniquely determines the scalar product, then how we began to understand the bridge with orthogonal polynomial. Historically, you see. Historically, the things went in the opposite direction. First, there was the definition of boson for space. Then, this was 1993. Then, with Lou, we discovered this interactive for space. And only in 1998, that theorem came. And that theorem motivates general, absolutely general definition. You see? So what is interacting fog? Interacting fog is the most general Hilbert space or pre-Hilbert space in which you have an orthogonal gradation and a creation. The orthogonal gradation in particular can be the orthogonal polynomial, but not all interacting fog spaces are orthogonal polynomial. There are many important physical examples in which our lectures only consider orthogonal polynomials. Interacting fog spaces which are orthogonal polynomials. So it's clear now.
So if it is exponential vectors that
the exponential vector, you must say for which omega. We will arrive to this. We will arrive to this. We have exponential vector in interacting. And we have exponential vector in and we have exponential vector in orthogonal. But they are not the same as the boson exponential vector. The boson are very special. Why? Because the exponential vector, they depend. So you see, in one variable, we know from the Jacobi that the orthogonal polynomial in one variable, in fact this is the Jacobi plus Pavarti lemma, they are completely classified by two sequences. And the notion of exponential vector depends on omega n. The general notion. The traditional notion is only for boson. Is only for Fermi they have never considered. But of course you could define. But is not why. Well, for Fermi would be identically the vacuum. Only the vacuum is exponential vector. Because you have alternating products, not tensor products. This is not so bad. In fact, in physics, exponential vector only for boson. Here, for any measure in the stochastic and probabilistic quantization. Okay.
So,
this scheme, I think, is not in the notes.
yes.
But maybe if you are interested, I should include a few this the preservator, you can only recover symmetric meshes with all odd moment zeros. You don't cover all probability meshes. So you miss, for example, if you take the square of the Gaussian, you cannot represent because it's not symmetric. Okay? And that is why in physics they found so many difficulties for the definition of the square of a boson field. There is a famous theorem of a very famous mathematical physicist called Segal who says the square of the boson field cannot exist. Why? Because he wanted to represent the square of the boson in the boson space. But now we know that there exists a square of the field. And this is called quadratic quantization. And quadratic quantization is orthogonal polynomial, which are the random variables corresponding to quadratic quantization, Meissner random variable. And which are the commutation relation of the quadratic quantization is not isotope. It's another very famous Lie algebra of mathematics. It's SL2R.
Yeah.
So you have the full picture.
Okay. If you are online, if you have questions, please write your questions so that we can read out.
This extends to supersymmetry.
That's the question about supersymmetry.
Yes, I know very well.
Up to supersymmetry.
In fact, supersymmetry comes very naturally in the theory of orthogonal polynomial and in stochastic, in probabilistic quantization, because we, as I insisted this morning, we have the multiplication table, not only the commutator. So we can do commutator, but we can also do anti-commutator, and we can also do a combination of the two. For example, in Bernoulli, the anti-commutator naturally appears. In Gaussian, commutator naturally appears. But you can do combination. Combination is supersymmetry. So, also supersymmetry is probabilistic. It's generalized by probabilistic.
So, Prof, I was just passing a comment that these results are very many years of consistent hard work done. For example, this is the 46th conference we are holding here. Yes, we are lucky to be able to host it.
Yes.
And I'm sure you congratulate us for very successful hosting. But in all the years that this has been done, you are involved. Now, how does your involvement help the revolution of this area of mathematics?
It is a, well, I should, it's a long story. Maybe I should, in the tutorials, I can devote a lecture on the story, how it happens. Everything began with how we arrived with Lou to this notion, interactive forces. Everything began from this. How did we arrive in a very, from pure physical problem? One of the most important problems in physics was to extend the quantum electrodynamics going beyond dipole approximation. All modern optics is based on dipole approximation, which is in some sense a very rough mathematical approximation. And with Lou, we had this was happening in 1991, 1992. The first result was 1991. And we began to attack this problem. And eventually, after 2 or 3 years of very hard work, we were able to solve, but we met a very strange structure, which we were very complicated. And we, in order to understand this complicated structure, we decided to axiomatize it. Which axioms? can describe this. And these axioms are what I told you. Okay? So, from the very, very rough and very complicated problem, the notion of interacting for space was born. About 5 years after, with Ezekiel, we noticed that this theorem that I have written here. And this was the beginning of probabilistic quantization. This theorem, because that made the bridge with the polynomials. This bridge with polynomials in one variable. To make the bridge with polynomial in many variables, I told you that in many variables it's not true that all interacting for space they come from orthogonal polynomials. So the problem was how to characterize those interacting for space that come from orthogonal polynomials. From 1998 to 2016, we attacked this problem. Eventually, we could, and the solution was given by the multidimensional Favard lemma that I mentioned. So the logic is this.
So, my whole last question is, how does this connect with the moment problem?
It is independent of the moment. Why? Because the moment problem can be formulated by saying in one variable, pay attention. In many variables is more similar but more complicated. In one variable, the moment problem is saying, if I give you the two Jacobi sequences, can you describe all probability measures? Can you describe all probability measures which are compatible with the two Jacobi sequences that I give to you?
Okay.
And, however, when I give you the Jacobi sequence, there are many probabilities, so we don't care the moment. The moment problem is not important for us. Of course, when you go in more subtle results, it will be important. That is, if you have uniqueness, it's important. But all the theory that I have developed up to now doesn't care. Even if the moment problem is not unique solution, all the theory that I have developed continues to work. Because we work on the state, and the state is uniquely defined by the moment, by definition.
Yes.
The probability distribution is not uniquely defined. But the state on the polynomial algebra is. Okay.
So let me ask a question concerning this theory.
The theory.
Yeah, I didn't see you solve any differential equation. What was the intuition behind having this category of interacting for space with category of orthogonal polynomial in one book?
You want to have explicitly what it means. You see, the category is important because you can formulate this theorem in a more precise way in the following way. Let me take a measure. I have a random variable x. Remember, this is equivalent to give the probability distribution quite simple. Alpine is identically simple. Okay? Now, take the symmetric Fock space. Take the one-mode interactive Fock space. Associated to the sequence omega n. And we call it like, use the same notation of Professor gamma of omega n. Remember, what is this? This is, by definition, orthogonal gradation. N is in n, and C multiplied 3n. Okay? Then, let us take the space L2 of this probability distribution of the random variable x, L2 of R. Okay? Then, the result, to say a category isomorphic means that there exists a unitary isomorphism which has the following property. U is unitary isomorphism of, you can say also, this is true also for pre-Hilbert spaces. And it has the following, the category enters in this, because of course any separable Hilbert space are unitary isomorphic. This is a trivial isomorphic. But what is a canonical isomorphic? And we have the following problem, that the orthogonal, the mu orthogonal polynomial phi mu n by the unitary isomorphism go to phi n. So you see, we go L2 space interacting force. This is the interacting force. One mode. One mode because it's a gradation is one dimension. Second, and this is most important, if I take the, here I have the usual position operator of quantum mechanics. Qf evaluated in x is x f of x. And here I have the random variable x, multiplication by x. Multiplication by x. Then, which let us call, in this case, I will call m of x to be, to specify that it is an operator. Okay? So, then, if I start from this space, so if u goes in this direction, then obviously you start, the adjoint will go the other direction. So you start, then I apply the usual quantum position operator, and then I go back with u, and I find my random variable. Then, this means gradation reserving. This implies gradation reserving. And implies that that u of the constant function equal to 1 is equal to the vacuum. See? And this implies that u dot u star maps position operator into multiplication by random variable and preserve the gradation. And that is much. These three properties uniquely specify the unitary isomorph. There exists only one unitary isomorph with this property. But for two separable space, there are uncountably many isomorphs. Because I can choose an uncountably many different ways the orthonormal basis. Okay?
So I don't know, are there any questions? Okay, so please let's give Professor Akadi a round of applause. Thank you for this project. So now we go for lunch to come back at exactly 5 minutes to 3. Please, we should be seated 5 minutes to 3 p.m. Okay? Thank you very much. So those online, at 3 we'll start the next